A single Cloudflare engineer spent $1,100 on AI tokens, and in 7 days rewrote 94% of the Next.js API from scratch. The result builds 4 times faster and ships bundles 57% smaller than the original. That number, $1,100, is roughly what a mid-level developer costs for 4 hours of work. Except this produced an entire web framework. Today we're covering that story and a separate but equally significant shift happening in robotics, where a new class of AI model is collapsing the entire perception-to-action pipeline into a single architecture. Between February 13th and February 20th, 2026, Steve Faulkner, an engineering director at Cloudflare, used Claude Opus 4.6 through Anthropic's Claude Code tool to rewrite the public API surface of Next.js. The project is called Vinext, V-I-N-E-X-T, and it's a Vate plugin that re-implements Next.js routing, server rendering, the Next/star module imports, the CLI, and pretty much everything else developers interact with when they build with Next.js. The motivation was practical, not theatrical. Next.js uses an entirely bespoke build toolchain, which makes deploying it anywhere other than Vercel, the company that maintains it, a painful exercise in reshaping build output. Cloudflare, Netlify, AWS Lambda, all of them have struggled with this. Faulkner wanted a clean re-implementation built on Vite, the popular open-source build tool, so the output would be portable. The process ran roughly 800 sessions with Claude Opus 4.6. Faulkner spent a couple of hours up front defining the architecture with the model, what to build, in what order, which abstractions to use. Then it became a loop: define a task, let the AI write the implementation and the tests, run the test suite, merge if it passes, feed the errors back if it doesn't. The final project ships with over 1,700 Vitest unit tests and 380 Playwright end-to-end tests, full TypeScript type checking, and linting. The performance numbers are striking. Vinext covers 94% of the Next.js 16 API surface, app router, pages router, middleware, server actions, streaming, incremental static regeneration, all of it. Builds run 4.4 times faster using Vite 8 and Rolldown, and the output bundles are 57% smaller. One particularly clever feature is what Cloudflare calls traffic-aware pre-rendering. Instead of pre-rendering all pages at build time, Vinext queries Cloudflare's traffic analytics and generates only the pages that actually receive visitors. For a site with 100,000 product pages, that typically means 50 to 200 pages covering 90% of traffic, which cuts build times from hours to seconds. The current deployment target is Cloudflare workers, but about 95% of the codebase is pure Vite, with no Cloudflare-specific dependencies. The team got a proof of concept running on Vercel in under 30 minutes. The core implication is blunt: if your competitive advantage depends on implementation complexity and your test suite is public, you've published the blueprint for your own replacement. Next.js represents years of work by dozens of engineers at Vercel. It is one of the most widely used web frameworks in the world, and one person rebuilt its entire public surface in a week, for the cost of a decent laptop. That changes the math on build versus buy decisions, on competitive moats, on what a small team can credibly attempt. This also lands differently, because it's infrastructure code, not a demo app. Framework-level development, routing, server-side rendering, static generation, middleware, is precisely the kind of deep interconnected work that was supposed to resist AI automation. The argument was always that models can write functions, but they can't architect systems. Vinext is a direct counterexample. The quality gates, 1,700 unit tests, 380 E2E tests, type checking, linting, are exactly what you'd expect from a human team. For anyone building a startup or running a small engineering team, the takeaway is quantifiable. The leverage ratio on skilled engineers, using agentic AI tools, just shifted by an order of magnitude. One person with clear architectural judgment and a capable model produced a framework-grade project in 168 hours. Vinext is still experimental. It's less than 2 weeks old and hasn't been battle-tested at scale. The things to watch: adoption numbers over the next few months, whether other platforms besides Cloudflare workers start officially supporting it, and most importantly, whether Vercel responds by opening up Next.js build pipeline, or doubling down on their proprietary toolchain. This is also a template other teams will copy. Expect to see more framework-level rewrites using the same pattern. Comprehensive test suite plus capable model equals near zero re-implementation cost. So AI agents just compressed years of software infrastructure work into a single week. Meanwhile, in robotics a similar kind of compression is happening, but instead of collapsing development timelines, it's collapsing entire engineering pipelines. A new class of model is merging what used to be 3 or 4 separate systems into one, and the research momentum behind it is enormous. Vision Language Action Models, VLAs, are becoming the dominant architecture for robot intelligence. At ICLR 2026, one of the top machine learning conferences in the world, researchers submitted 164 papers on VLA models. That number alone signals a research field that has hit critical mass. To understand why this matters, you need to know what came before. Traditionally, building a robot that can interact with the real world required at least 3 separate systems. A vision system to perceive the environment, typically a convolutional neural network processing camera feeds. A language understanding system so the robot can interpret instructions. And a control system, the motion planner and motor controller that translates decisions into physical movement. Each of these was a separate model, trained separately, integrated through handwritten glue code, and debugged independently. Getting all 3 to work together reliably was a nightmare of systems engineering. VLAs collapse all 3 into a single model. One neural network takes in camera images, processes natural language instructions, and outputs motor commands. The same architecture that reads the scene also understands what you asked it to do, and generates the arm movements to accomplish it. The major implementations are coming from the biggest names in tech and robotics. Figure AI's Helix model powers their humanoid robots. NVIDIA's GR00TN1 is designed for general-purpose robot control. Google DeepMind's RT series pioneered much of the early work. Physical Intelligence has their Pi series models. And on the accessible end, Hugging Face released SmallVLA, a lightweight version designed for affordable robotics hardware. At ICLR 2026, the accepted papers reveal 3 emerging architectural paradigms. Early fusion models that blend all modalities from the start. Dual system architectures that separate fast reactive control from slow deliberative reasoning. And self-correcting frameworks that let the robot detect and recover from its own errors. Several papers also explored diffusion-based action generation instead of purely autoregressive approaches, which produce smoother, more efficient movement sequences. One notable paper, XVLA, introduced a cross-embodiment approach, a single model that can transfer learned behaviors across different robot body types, now integrated into Hugging Face's LaRobot platform. The analogy that keeps surfacing in the research community is the transformer moment for natural language processing. Before transformers, NLP was a patchwork of specialized models, one for parsing, one for translation, one for generation. Transformers unified the stack, and within a few years the barrier to building language applications dropped from PhD-level expertise to an API call. VLAs are doing the same thing for robotics. When perception, reasoning, and action live in one model, the integration problem disappears. You don't need a team of specialists to wire together separate vision and control pipelines. You train one model end to end, and the system learns to coordinate internally. That dramatically lowers the barrier to building robot applications. The cross-embodiment work is particularly significant. If a single VLA can transfer skills across different robot body types, it means training data from one platform becomes useful on another. That creates a flywheel. More robots generate more data, which improves the model, which works on more robots. The field is still early. Researchers themselves acknowledge the lack of standardized benchmarks for comparing VLAs across simulation and real hardware. But the architectural direction is clear. Robotics is consolidating around a unified model paradigm, and the teams building on it now will have a significant head start. The things to track: whether standardized benchmarks emerge that let the field compare VLA models fairly across simulation and real-world performance. Watch for Hugging Face's SmallVLA adoption. If affordable VLA models start showing up in hobbyist and small team robotics projects, that's the democratization signal. And keep an eye on Figure AI and NVIDIA's deployment timelines. The research papers are stacking up fast, but the gap between conference demos and robots that reliably work in unstructured real-world environments is still the hardest part. $1,000 and a week rebuilt a major framework. 164 research papers are converging on a single architecture for robot intelligence. The cost of building complex systems, digital and physical, is dropping faster than most people's mental models can keep up with. The question worth sitting with: what becomes possible when the things that used to require large teams and large budgets simply don't anymore? If you want to keep tracking that question, subscribe. We cover AI and tech news every day. See you in the next one.